believe some professors here taught you before.
Oh yeah, sure.
Okay, give 1 more minute, we start, okay?
Okay, sorry. Should I start to share my screen?
Yes, you can. It's perfect, fine, yeah.
Screen. Oops. You can all see it, right?
Yeah, perfect. Okay. So hi, good afternoon, everyone. Today we have the Dr. Liu to give a talk on natural language processing-based knowledge sharing and evidence retrieval of clinical studies. So Dr. Liu right now is postdoctoral research scientist at Columbia University from Department of the Biomedical Informatics. So Dr. Liu received his PhD from computer science at New Jersey Institute of Technology. And also he received his master degree in electric engineering from Columbia University. And most important, Dr. Liu received his bachelor degree in ECE from our school. So he's our alumna. Okay, let's welcome Dr. Liu to give us a talk.
Hi, everyone. Thanks a lot for the... Okay, yeah, got it. Yeah, thanks for the introduction. I'm Hao Liu, and now a postdoc in Department of Biomedical Informatics at Columbia University. My research and publications mostly focus on this two kind of research area. The first one is the clinical informatics, where I did a lot of research on optimizing clinical trial design, evidence retrieval, and scientific claim verifications. We also did some COVID-19 related research, such as COVID-19 trial founder, and also we annotated some COVID-19 related clinical trial data. For the other topic, which is more about oncology enrichment and quality assurance, which are the most research I did in my PhD study. So today, in today's talk, I will mainly focus on the natural language process-based knowledge sharing and evidence retrieval of clinical studies. I will start with introducing some background about evidence-based medicine and also clinical trials, which is a very important source of providing evidences. Also, I will introduce like the two kind of NLP-based application we developed to for the two topics here, optimizing clinical trial design, and another one is evidence retrieval and scientific claim verification. The first application, we call it clinical trial knowledge base, which is short for CTKB. And the other one is a clinical scientific claim verification system. We call it CLEVR. The first one is published in JBI. The second application is in submission to JBI. So what is evidence-based medicine? So evidence-based medicine represents integration of clinical expertise, patients' values, and best available evidence in the process of making clinical decisions related to patient health care. So imagine a clinician is trying to providing or design a treatment plan for pancreatic cancer patients or breast cancer patient. He or she will probably combine what he knows and what the patient wants and what are the best research evidence that in the medical literature. Right? So it is very important to, evidence-based medicine is important to improve the quality of healthcare and also to achieve patient satisfaction. So when we talk about the evidence, of course, there are many resources to get evidence. So here is on the right, I provide a pyramid of evidence. So you can see like here in the randomized control trials sit in the middle of here, but it sits on the top of unfiltered information, which means this information is not post-processed with experts reviews or something. It generates direct evidence from using well-designed clinical trials. So normally the results, the outcome from randomized control trials are widely regarded as a reliable source of most valuable evidence. So what we are trying to do here is how to get the best evidence from clinical trials, and also how to optimize the design of clinical trials to guarantee, improve the quality of the evidence generated by the randomized control trials. So with this in mind, you can, if you think like how we can generate medical evidence from clinical trials, the practical process of this conducting clinical trials is quite complicated, but I simplified it into like the three main components here to help you understand the idea. If you're imagine you're a doctor or like a trial investigator, or like a drug company, you try to investigate whether hydroxychloroquine can help treat COVID-19 patient with diabetes between 40 to 60 years old. So here you will try to the first thing you need to do is develop appropriate eligibility criteria for participants to participate in this treatment study. So here I know maybe for those who are not familiar with the clinical trial, you may not know what is the eligibility criteria. So here, using your common sense, you can think of like who should be eligible for this trial. If I'm asking this research, if I want to conduct a clinical trial focused on this research question, then I probably recruit COVID-19 patients, and the patient must be diagnosed with diabetes, and the patient should be in the age between 40 to 60 years old, right? So actually, eligibility criteria is used by researchers to determine the eligibility of a participant in a specific research study. So we have inclusion criteria, we have exclusion criteria. Given by their name, you already see like inclusion criteria is used to rule in a participant. For example, I want patient between 40 to 60 years old, right? Exclusion criteria is to rule out a participant. For example, I don't want maybe a pregnant woman to enroll in my COVID-19 trial because it may interfere with the treatment, with the outcome of my study. So to give you a sense of what our trial look like, I should bring to here. Here, this is a trial on COVID-19, which is published on clinicaltrial.gov. Actually, FDA approved those drugs. For FDA to approve any drug or treatment or therapies, they have to go to they have to register. They have to go to this process of clinical trials and register those clinical trials in the clinicaltrials.gov. And you can see here is a summary page of this clinical trial. And you can find all the meta information about this clinical trial. Most importantly here, the focus of my talk here is all the inclusion criteria and exclusion criteria here. You can see there are the rules to let you know what kind of patient or participant we want and what kind of patient and participant we should rule out. Okay, continue. Yeah, is there any question? Did I hear anything? Oh yeah, okay, sorry. Continue with this. So you can see we use inclusion of exclusion criteria to select participant or patient to, enroll in our clinical trial. So for trial coordinators, they will need to review those eligibility criteria to decide who are eligible for this trial. And for like a lay person, like all the patients, they can look at the clinicaltrial.gov for each trial to decide whether they are eligible for that. But they still need to contact the coordinator to officially decide whether they are eligible for this trial or not. So this is a process of trial and patient matching. So this normally it's a manual process, and it's a really labor demanding. So well, this here is a place we say, okay, what if we can automate this process, right? Here the last is evidence retrieval. So you can, after the trial are conducted, normally like in 2 or 3 years, the trial are completed. A trial is completed, and then they will publish the result into the clinical literature. So that become evidence for some research questions. For example, if a clinician comes in and asks a question, does treatment with hydroxychloroquine improve clinical outcome of adults hospitalized with COVID-19? This is actually a research question, relevant or not. So this is the background of this process, how we generate evidence from clinical trial, and how we can appraisal and synthesize all the evidence. So, but the barriers, of course, all those are manually conducted, and what we want to do is, how can we teach the machine to do that? How can we automate this process, right? So the first difficulty we are facing with is called information overload, which is to automate patient trial matching. We have a great gap between the clinical trial recruitment and access to available clinical trial opportunities. So for each year, we have more than 11,000 trials are published, and only 40% patients feel confident in finding appropriate
this is also
trials.
important. This came up suddenly.
Could be because that for layperson, if you are looking at those eligibility criteria, you don't know what you are looking really challenge for patient matching, or how can we pass all the eligibility criteria, convert it into like queries, and then automatically query the electronic health record to the eligible patients for a trial. So this actually
it's going to
what we appraisal, we mean try to conduct the scientific claim verifications. So let's first focus on the first one, is optimizing the clinical trial eligibility criteria design. Here, by optimizing, we mean we want to have a parser to do automatic eligibility criteria passing, and by passing all the eligibility criteria, we can construct a knowledge base. And after we have this knowledge base, and we can support automatic cohort identification. I will elaborate on this process in a minute. Yeah. So this part is actually focusing on how to optimize the clinical trial design, and the second part is how can we optimize how can we improve the evidence retrieval and appraisal. So the first one so this brings us to the first application, NLP enabled application. We named the clinical trial knowledge base. So I want to, before I move to the technical details of that application, I want to give you more idea of how the automatic cohort identification works. So imagine you have this clinical trials, which is impact of rheumatoid arthritis on the course of type 2 diabetes during a longitudinal follow-up of 5 years. So this trial, we have some inclusion criteria, which is like the first one, we have a type 2 diabetes with HbA1c is greater than 60.5 percentage. And also we have like other criteria, fast glycemia or glycemia after 75 microgram glucose ingestions, include criteria like that. And on the other hand, we have EHR database. And in that EHR database, we have patient data like the ID, the age of the patient, visit ID. So also, in that visit, a patient could be diagnosed by the clinician that he or she had the type 2 diabetes. And we have some lab tests, fasting glycemia, for example, greater than 8.5 millimole per liter, right? So those are the patient data in our EHR database. So what we want to automate is how can we automatically convert those criteria to queries, and then so to query the EHR database, and then we return some eligible patients. So the queries can be simplified into multiple simple queries. So we can repeat this process. What are the patients eligible for the first criteria? What are the patients that are eligible for the second and the third? And then what are the patient that are eligible for all the criteria? So we can, the idea is to automatically convert the criteria into simple queries, and then do some post-processing to find out who are the patients that are eligible for this criteria for this trial. But the devil's is in the details. So even though the idea looks quite simple, but actually when you really implement this system, it becomes more complicated, and a lot of small things we need to address. For example, here is the pipeline, how we automatically perform the eligibility criteria parsing, and also how we convert that into convert the queries to query our EHR database to identify patient. So if you have the eligibility criteria here from this clinical trial, we first need to do some named entity recognition to identify all the concept, the measurement, and the procedure, and some attributes, for example, temporal attribute and values. So using some NER to identify those entities. And after that, we need to do some normalization. For example, body mass index is the same as BMI, right? This kind of we need to standardize some medical concepts, and also we also normalize the attributes. We need to know which temporal attributes this one associated, which entity this temporal attribute is associated with. And for this value smaller than 7 days, we should normalize this value with the mean and max values, things like that. And all this normalization, we follow a common data model. We call it OMOP common data model. So, all the medical concepts are standardized using some controlled vocabulary. So it's consistent vocabulary. And after we normalize those, we extract those normalized entity relationships and values from this raw text. We can follow some templates to generate SQL queries to query our EHR database, right? So then we can have the all the eligible patients that satisfy those eligibility criteria. And on the other branch or other route, we have all those normalized attribute or concept becomes the structured eligibility criteria. So we can store those structured eligibility criteria into our knowledge base. And this knowledge base actually can guide how we generate the query to query our EHR database. So we know like that our machine does not always work as we wanted. So what we do is before we generate the queries, we provided a user interface for clinicians or physicians to review and update the normalized entities or attributes. So all the eligibility criteria can be reviewed by domain experts to fix some errors, some NER error or relationship bounding errors, so that we can get more accurate queries and more more accurate cohort identify, more suitable patient for this trial. So
I have a question, Hao.
Yeah, sure.
Yeah, here you mentioned for the inclusion criteria, right? And then you base on you standardize them, normalize them. So
yeah.
You try to use, let's say, when you generate eligibility criteria and all those inclusion rules. So when you do that, do you consult the ontology?
Oh no. Actually, it's really depending on who is designing the trial. Like for I will say for doctors or the drug companies, when they design this trial, clinical trial, if they don't have any knowledge of ontology, or they don't rely on some knowledge of terminology or medical terminology, they won't have this awareness. I need to formulate my inclusion criteria to make it bound to any a medical concept in, for example, SNOMED or UMLS, right? So I will say the background of the trial designers really diverse. So normally they will just provide the raw text, free text, and without the awareness of any ontology or medical terminology. So that really,
it's very unfortunate, because most pharmaceutical company they do use a pharmaceutical ontology for all things. So if they can, let's say, consult the ontology, that later will make the
yeah, of course. It's making our job easier.
Much easier.
Yeah.
Okay.
Yeah, that's true. Yeah. So that's a great question, and also brings us to why the natural language processing is important when we try to post-processing those eligibility criteria, standardize those. For example, we have this raw text, free text. This could be when the doctor or trial designer designed this trial, they just put this whatever they want in what they comfortable with. So just describe the criteria. So for example, BMI and mechanically ventilated for smaller than 7 days, they are quite flexible of generating or curating those rules. So it is then our job, or NLP's job, to automatically determine, okay, BMI is a measurement, 18 point to 30 point kilometer meter squares is a value attribute. These are a mechanically ventilator is a procedure, temporal, smaller than 7 days is a temporal attribute, right? Things like that, drugs, observations, and even negation cues here. So these are, if you have any experience in NLP or named entity recognitions, on the right-hand side, in this figure, the Sesame Street, I list some the most popular transformer-based or a deep learning neural network-based models, pre-trained models, BERT, Elmo, BERT and PALS, Arenies, Groovers. So those are popular deep learning models that can achieve this new state-of-art performance on NER. So actually, in our group previously, there's a researcher Yuan. To give him credit, he already created this criteria query, which it can automatically take the attribute criteria and perform the on it. So let me demonstrate a little bit, if time permit, how this system works. So for here is you can try. Feel free to try this website. The URL is on the top. Here, like for each clinical trial, we have a unique ID. Here, I just put a demo ID here. It when you click on this extract criteria, it automatically pulls the inclusion criteria and the exclusion criteria from clinicaltrial.gov. And here you can see the inclusion criteria is listed on the left, and the exclusion criteria is listed on the right. And let's perform the attribute criteria parsing, and let the NER module work and the relationship identification module work too. Let's ignore that for now. So you can see after we click on the generate cohort, we are not there yet, but you can see like here we identify some conditions measurement from the attribute criteria, and also same here we identify some conditions, the age, demographic, and we bound it with a value here. What you just saw is because we are query a fake patient database, so if we use all those criteria to query that database, we don't get anything returned. But if let's say if we relax this criteria a little bit, let's say we uncheck this criteria and see how many patients satisfy our criteria here, we can see we got 259 patient returned from this SynPath 1000 patient database. We have like 259 patients satisfy our criteria. So let's say if we relax this age criteria again, let's see how many we get. So we have 278 patients, and the demographic information about those 278 patients are listed below. So you get the idea, how the NER plays a role here. We use the deep learning model to automatic identify the patient, identify all the entities and the attributes, and here like the language model where temporal attribute, what's the max value. And also for the concept, for example, the mechanically ventilated, we normalize it into our artificial respiration, to map this procedure to this standardized concept, medical concept. Well, this apparently it's very difficult to do the concept normalization. So for the best performance we get here is 0.614 for the precision. And another one is the negation, when you have a not, does not. We have our module. We trained a model called NEGBERT based on BERT, so to automatically identify negation cues and also the scope to identify the keywords that to trigger the detection of negation and what the scope of this negation applies to. So after this normalization, we store this structured attribute criteria to this we call the clinical trial knowledge base. This actually, here is like the system component of the clinical trial knowledge base we created. You can see there are multiple layers. From the very bottom, we have attribute criteria in free text format we collected from clinicaltrial.gov. After run the criteria query, where we perform the automatic parsing of attribute criteria and normalization. We store all the structured attribute criteria and the trial meta information into MySQL database, and we categorize those structured knowledge eligibility criteria into different knowledge domains. And then we provide web components to support some aggregate analysis and also some visualizations. And this system is available at this URL, ctkb.io. I know you guys don't want to look at the text here, but I think I basically covered this. And for those, I want to demo two use cases of CTKB. The first one is, after we store all the eligibility criteria, structured eligibility criteria, we can provide two aspects for you to look at the aggregate analysis. First, we want to focus on criteria, one single criteria, see how this criteria is used among different clinical trials, and we can divide it based on the conditions it is used and based on different phases of clinical trials. The second one is on cohort definition. Here, the focus is on one disease, so one condition or one disease. So imagine if you want to know what are the most frequently used eligibility criteria for type 2 diabetes. We provide this functionality so that you can just search type 2 diabetes and get all the criteria used ranked by their frequency. And after that, you can pick what criteria you want to use and to generate cohort queries to automatically return who are the eligibility patient from our EHR database. So just to demo that, so you can visit this website ctkb.io, and if you click on the criteria summary, here I select our criteria. The default criteria is called BMI, body mass index, and you can see here we provide the statistics about this criteria, how many times, how frequently it is used. It has been used in about 36,000 trials, and it has been used as inclusion criteria in about 25,000 trials, and about 10,000 trials as exclusion criteria. And based on the frequency of this criteria used, it's ranking as 11 among all the criteria. And also, since BMI is actually a measurement or it is bound with a value, we draw the value distribution. For each trial can have a different BMI value specified. So that will be one count of this, this value of BMI have been used once. So if we, draw this value distribution for, let's say, 25,000 trials, we get how the BMI value are used among all the, trials. And also here, we want to see, okay, which condition, which disease use BMI most frequently. So here, sorry, I should so here we ranked how frequently BMI is used based on the condition, based on the disease. You can see here, in diabetes, in type 2 diabetes, BMI is used as inclusion criteria about 215 times, and it has been used obesity around 1,495 times as inclusion criteria, right? So we rank those the frequency of criteria based on their frequencies by their disease domains. And here is the frequency this BMI is used based on how frequently it is used as exclusion criteria. You can see there are multiple diseases here. Its use is ranked by the frequencies, and also we draw the pie chart of how this BMI is used based on the phases of clinical trials. So how frequently BMI is used as inclusion criteria, among those 4 phases among those trials with different phases. So another angle of looking at of our clinical trial knowledge base is, what if I want to know what are the frequently used criteria for type 2 diabetes or for breast cancers, things like that. So the focus is now we are not looking at the individual criteria, but we are looking at one single disease we are interested into. For example, here, I want to know what are the frequently used inclusion or exclusion criteria about the type 2 diabetes. So here, all the inclusion criteria are ranked by their frequencies. Actually, type 2 diabetes is frequently used inclusion criteria because, most of type 2 diabetes trials will specify, I want patients that are diagnosed with type 2 diabetes. And other like a BMI, metformin are frequently used criteria. HbA1c is also frequently used. And also there are, exclusion criteria. For example, pregnant type 1 diabetes are frequently used as exclusion criteria for type 2 diabetes trials. So for example, if I want to just select multiple criteria for example, if you are designing a new trial for type 2 diabetes and you want to refer to previous trials, what are the frequently used criteria I can borrow or I can refer to? So here is the table providing that kind of information, and you can just select those criteria and say show selected criteria. And actually the next step is to direct you to the Atlas, which is a cohort, which will automatically convert those eligibility criteria into templates. And after you get those templates, you can have send that SQL query to EHR database to get eligible patient. But unfortunately, our connection with Atlas is not stable as they constantly updating their API. So I cannot demo that process. But I guess the idea is after you select some eligibility criteria, those set of eligibility criteria can be imported into this system called Atlas. And this system can take care from that. To generate a cohort and also querying patient EHR database to get you all the eligible patients for the criteria selected. So we think this system can assist CDKB, by connecting all the structure, by reusing the knowledge of eligibility criteria from previous clinical trials. CDKB, our system can, help estimate the potential cohort before the start of a trial to facilitate early trial planning and, also to provide the protocol feasibility analysis. This is the study of this is the application of how we use NLP-based method to optimize clinical trial design. And the second one is the second application I'm going to talk about is evidence-based retrieval and a subtask of evidence appraisal called scientific clinical verification.
By 145. 145
So if we rewind a little bit back to when I talk about how clinical trial generate evidence. So after a clinical trial is published, the result is published. We have those evidence in the clinical trial literature. So we want to automatically to retrieve evidence and try to conduct some evidence appraisal or computation. So if we have the ability to do that, it actually assists those scientists or clinicians to conducting systematic reviews, because you are given, for any research question, you are given a set of relevant evidences, and then you can do your systematic review, evaluate the how those evidence is relevant or like a help to justify the veracity of your research questions. And also, if you're having a bunch of evidence together, by review them, you will know the status of a consensus of those of this research topic. Like a lot of evidences are towards justify your claim, and another a small set is just contradicting your research question, right? So you will get a sense of what the status of a consensus and the maturity of a specific research topic. So this is just want to to know more about the motivation behind this work. Our typical trial workflow is we recruit patient, we record data, we analyze the data, we report the result, and the result can be published in various places, right? ClinicalTrials.gov, PubMed, for some regulatory documents, and some places they will do like Cochrane, they will do risk of bias and analysis and effect size analysis to determine the quality of the evidence. Since this tells you like searching for evidence is difficult because actually it's spread across the different places. And to formulate a really good, to really search for good evidence, or like to really search relevant evidence, clinicians has adopted a framework called PICO. So actually, when you conduct your search for evidence, you actually formulate your research question with the sense of these PICO elements. P stands for population, I stand for intervention, C stands for comparison, O stands for outcome. So for example, when the clinician or physician is interested in whether patient undergoing abdominal surgery, does really chewing gum help or not? Chewing gum or not chewing gum is helping the post surgery ileus. So that will be they will like formulate their research question like that to make sure like the query make sure the query is focused on those PICO elements. You will see later how these PICO elements play a role in our system, Cleaver, how this can help improve the the result, evidence retrieval result.
Please step aside and let the customers off.
I think I can mute. Do you want to mute? Okay, so I probably don't have enough time to cover those challenges, but you already see like for evidence retrieval, medical evidence retrieval and appraisal, there are multiple challenges. In retrieval, medical evidence are in the form of unstructured text, and the rapid expansion of the clinical literature has increased the burden, make it really difficult for clinicians to keep up with the pace. So it's really hard for them to know what is the most advanced findings or results in the literature, right? And the challenge in medical evidence appraisal is like manual synthesis is difficult, is troublesome, and clinical results share platform, the clinical results share platforms for structured evidence, but it's hard to scale. And we have like automatic medical evidence, entity recognition, unable to locate primary evidence. So for those works, just identify the entities in the literature, but difficult to let which part, how they can combine to be considered as a evidence. And also some machine learning based is lack of explainability, right? So it's hard to interpret the result, even though they and also the inference they do there is very simple. Well, there's a lot of challenges here. So our work is not to try to tackle all those challenges, but to first facilitate the retrieval of evidence, and then do some inference on the retrieved evidence towards the research question or the research claims we are interested in. So, but the idea being like searching for best evidence is more difficult because that involves in domain experts domain knowledge to decide to do more like inference, to decide to do more synthesizing about which are the best evidence, what evidence should I trust or not. So in our in our work, what we want to do is we want to automatically identify, we want to create a system to automatically identify relevant evidence from massive size of clinical trial studies to help clinician or researcher to get actionable knowledge and to inform their clinical practice. And here, can you see this? Yeah. The system actually is deployed in this URL. We don't have our domain name yet, so the system is deployed there. Cleaver, which is our system, our goal for it is to assess clinical trial study, provide evidence supporting or refuting our clinical research claim. But at this step, we have to admit that it cannot assess the credibility of the clinical study paper itself. But we, for some evidence we extracted from one clinical study, we can decide whether this evidence support or refute a clinical research claim. So this work is in the preparation for submission. And how does this system work? Let me give you here is a pipeline of this system we call Cleaver. So given our scientific claim, for example, here, hydroxychloroquine compared to this drug Arisromig improved clinical outcome for treating COVID-19 patient, right? So this is the claim from the user. Maybe it could be like clinician or scientific researchers. So this claim is given to our system, and our system already indexed some randomized clinical trial abstracts from PubMed, and by going through the 3 steps: abstract retrieval, sentence selection, and label prediction, we identify all the clinical trials that are these 2 trials has not enough information to determine whether it's whether it support or refute our claim here, but the other 4 studies support it, and the other 12 studies refute it. So our system identify individual sentences from each abstract and assign labels whether this abstract support or refute the claim based on the selected evidence sentences from those studies. And to show you the technical details of this work, you can see like all the RCT study, randomized control trial studies abstract indexed, and the indexing and the claims are, our system leverage the indexing and the claim to first do the abstract retrieval, which we use the BM25, best match 25, to select N candidates. This parameter can be specified by user. I think we choose 1,000 candidates abstracts, and then we use our T5 ranker. T5 actually is a sequencing to sequence model. It's similar to transformers in NLP field. So, but actually the sequence to sequence model outperformed the BERT-based model. So we use the T5 ranker to rank those N candidates, 1,000 abstracts, to select the top K abstract here. Here we used 25, K equal to 25. So we select the most relevant 25 abstracts based on the claim here. And then, we scan through all the sentences in those abstracts, and we use this T5 ranker again to rank the relevance score of each sentence towards this claim. So all the most relevant sentence is obtained to later to be used for label prediction. Here, after we select the we call rational, the most relevant sentence is considered as the rational sentences. So we pair that claim we have and the rational sentence here, and we pair this to send it to 3 deep learning models, and we for assigning labels whether this sentence support or refute that claim. So we ensemble 3 deep learning models to take advantage of each models. So each models may make their to take advantage of using all the features from those deep learning models, because single individual model can make mistakes and may have like its disadvantage in predicting certain kind of claim and sentence pairs. So we ensemble 3 deep learning models using majority voting to get the final label. So we ask 3 models to predict 3 different labels, and we take the majority voting to get the final label for whether those studies support or refute the claim. And I think here are some statistics about this Clever. Actually, we indexed around like a 189,000 RCT study in about 10 years from 2010 to 2021 from PubMed, and we invited 4 clinicians. Each of them like nominated 5 clinical related claims. So we verify those 19 clinical related claims using Clever, and we find out the Clever achieved over 78% of estimated accuracy for extracting relevant evidence, and about 80% of accuracy in label prediction in the Oracle setting, and in the open setting we have about 70% accuracy, getting the right label that the reviewers agree with. And we also test our system's generability by verifying some human curated COVID-19 related claims, and we found out our label prediction on the COVID-19 claims is actually pretty good. We have a micro average F1 equal to 0.92. Let me demo this a little bit. So the system is available at this URL. Here, I think I already have this open. Okay, here. Yeah, the system is deployed here. In the landing page, I provide some example claims you can try to let the system verify and get the result. Note that since we deploy this using Google Cloud without GPU availability, so verifying each claims could take about 5 to 10 minutes. So that is because we don't have GPUs, and all those deep learning model computations are very slow with the CPUs. But normally, when I tested, I have a GPU in my computer, so it's normally take about 15 to 20 seconds to run one claim. So I have this claim ran before, so I can show you. We don't have to wait about the 10 minutes. So here, the query I put in the Remdesivir compared to placebo and the Sendcare does not improve clinical trial for treating COVID-19 patients. Here, the search type I use Pickle, meaning I will, passing this, I will identify Pickle elements from this claim first, and then send this query to our system. And the deep learning model, we have a T5, Roboter, and PubMed BERT. If you choose all, this means you want to use in the ensemble to ensemble the result from 3 different models, right? So after you send this, submit this, wait for a while, and you can see the participant is actually COVID-19 patient. The intervention is Remdesivir compared with placebo or standard care. The observation is we want to see whether it improve or does not improve clinical outcome. So the outcome being clinical outcome. And the negation detection also works fine. It detects the not here, does not here, right? And also the scope is improve clinical outcome for treating COVID-19 patient. So the PICO element actually identify correctly all the elements from this claim. And after checking around those 189,000 clinical trial studies, we returned 9 studies potentially support this claim and 10 studies potentially refute this claim. So at here we list all the relevant studies. So actually we only predict the label for highly relevant and relevant studies. We can have some studies that are somehow relevant. You can see somehow relevant. Then in that scenario, we don't predict the labels for such studies. I want to show you some, let's see whether our system get it right. For this one, Remdesivir for COVID-19, this is a systematic review study. Our system claims it is highly relevant, and the label it predicts is a support. So let's open this study and see, this is the abstract of it. Here are the PMID of it. By using this PMID, you can access this study on PubMed. And so there was no evidence of a significant improvement with Remdesivir regarding all-cause mortality, clinical progression, or diarrhea compared to the there's no compared to the placebo or like a standard treatment. So actually this evidence we extracted support our claim because it found like a Remdesivir does not have a significant improvement. And for the refuted one, so if this study refute our claim, so that means it's actually found out the Remdesivir is useful compared to the placebo or standard of care, right? So here you can see like I think it is it takes sometimes we extracted 2 evidences. So actually I think it's probably read the second one has positive effect on clinical improvement and reduction of risk of this one. Even though the first one show that there's no skin on this. However, there's a however. Remdesivir had a significant effect on clinical improvement at the day 14 compared to placebo. You're probably, it taking into account of the second sentence, our system predict or refute. So we can look. I don't think I have enough time for this, but so you can feel free to play with the system. It may take a little bit while to run one single claim, but please bear in mind, like, you need to be patient for the result to return. Like, I already demoed that. So I think I can skip the inclusion and thank you for your time. And I'm happy to take any questions if you have. I'm right on time, right?
Yeah, you have time to the hall. Yeah.
Oh, yeah, I still have time. Yeah.
And conclude your talk.
Yeah, the conclusion is like, it's not like a conclusion for the 2 studies. It's just like, okay, you already, I think by demonstrating the system, you already see, how NLP play are important rules. All the NLP techniques enable the knowledge reuse and sharing. Especially in processing the information around the clinical trial studies, and also for evidence retrieval, for evidence-based medicine, we can leverage NLP to automate the medical evidence entity recognition, and also do a little bit do one more step, which is just classify whether the evidence is supporting or refuting, which we call it evidence assertion inference, right? So these are I think there are the basic steps towards evidence appraisal and evidence computation. Yeah, that's probably later on we can build on this the system we have here, the functionality we have here to support more advanced functions such as evidence appraisal and computation. Yeah, yeah, I think that's what I have for now. Yeah. And I'm happy to take any questions. And here's my email. And if you have any questions or like to collaborate, feel free to email me here. Yeah. Let's see. Should I stop?
Yes,
Okay.
you can stop sharing.
Okay. Yeah.
Yeah, I have a question. Like you mentioned, you use you assemble three deep learning model.
Yeah.
You eventually take the majority vote, right?
Yeah.
So how do you, let's say, select those three models based? You have the specific criteria because there's so many different deep learning models, right?
Yes.
Elaborate a little bit.
Yeah. Let me think. So for the in general NLP domain, they have this scientific claim verification, and people already fine-tune those two models, like the model Robota, right? Robota and the T5, they already achieve like the state-of-art performance using Robota and the T5 model. So that that give so given that, I think I should definitely include those two models into my our system here. And actually, I fine-tuned those two models using our data and to see that it's really outperformed other vanilla BERT model or even some variants of BERT like a BioBERT. But the PubMed BERT still have its own advantage. PubMed BERT is a little bit new. It's released by Microsoft. And actually, it achieved a very good performance in NER. The competition I won is actually based on PubMed BERT. So okay. I really like this model, and really, by fine-tuning it a little bit, it really can catch up with those other two models. And I see it outperform those two models for certain for certain classes in terms of precision recall and F1. So finally, I decided to use these three models, and based on my experience, that PubMed BERT model already outperformed the BioBERT, BlueBERT, things like that. So I keep one BERT model. Robota is really the based on the general domain state-of-art performance, and T5 is a different structure. It's a sequence-to-sequence model. I believe it has its own advantage compared to BERT-based model. So that's the reason I choose these three models. Yeah, of course, if you have time or bandwidth to fine-tune other BERT-based models or other transformer-based model, I think including more models could potentially improve the final performance. But the question is how, and whether it's efficient or whether it's cost effective. Yeah. Mm.
Okay, thank you.
Yeah, sure.
Any question from audience?
Yeah, I have a question. So first of all, thank you for the presentation. Yeah, so my question is related to your first work.
Yeah.
So you do the non-entity detections, normalizations, and then you do queries generations to automatically generate the queries to search for the candidates, patients for the clinical trial, right? So I saw that you already showed the performance for non-entity detections and also normalizations, but I just wondering how would you evaluate the performance for the entire system? So would you compare this with the, the human generated queries or, yeah?
Yeah, are you, sorry, just to like reiterate the question, how we evaluate the performance of the whole pipeline, right? The performance of the automatic cohort identification, right? Okay, that's a really good question. I think in this, well, in criteria to query, actually, we probably didn't report the final result of the cohort identification because, you know, the final step is linked to convert to send our SQL queries to a new system called Atlas, and through that system we can get patient the real eligible patients, right? For this, actually, we didn't. I don't think we evaluate that part because that first of all, the access to real patient data database is limited. Normally, when we do research, we always work with the synthetic patient database. So to actually get the real performance, yeah, we need expert to review the patient returned by the system to really check. But I will say for this is really hard to do because that, for a patient to be eligible for a trial or not, it's actually a little bit tricky, and because a patient could not, maybe a patient could be eligible even if it doesn't meet all the requirements in the eligibility criteria, because not all eligibility criteria are queryable or like are checkable using computer, like speak Spanish or like have somebody to come with you to the trial, right? That is difficult to evaluate. This makes the ground truth of the cohort identification really hard. And what we normally do is, I know, yeah, it's curious, how can we determine the real performance? What we do is I think in some of my colleagues design some metrics to assess the quality of the cohort returned by our system. They have a metrics to calculate the representativeness of this cohort. How distant this cohort is from real cohort, real patient, right? So they have a score on that. So of course, we want the returned cohort to have a higher score in that we call GIST, right? The GIST score, meaning it's if the higher score, the more represented, the cohort returns more similar to real world cohort data, right? So that GIST score can be used one metrics to evaluate the performance of the whole pipeline. But it's really hard to get the ground truth here, the golden standard here, because that's really depending on human performance. I think it's similar to information retrieval too. Normally you don't have the real ground truth. You only have like a small subset, like then you work with that. Yeah. Yeah, I hope that answers your question. Yeah. Okay. Yeah.
Okay. Any question for Dr. Liu? Yeah, Hao, thank you for the interesting talk. And I saw some students here, like just for your information. So Dr. Liu was our student. So you can continue, let's say, on the graduate study and pursue master or PhD in here or outside of the NYIT. Okay.
Yeah, that's true. Thank you for the opportunity. I really enjoyed this whole talk and the communication between the students or professor from where I graduated from. This is really a privilege or honor of me to give this talk, and I'm looking for collaborations or future opportunity to conducting research together or more communication together too. Yeah.
Sure.
Yeah, we'll keep in touch. That's
Okay.
HR.
Yeah.
Yeah, thank you.
Okay. Bye.
Have a good one. Bye.
You too.